So in part 2 of this lecture, I'll talk about bonds and chemical properties. So we'll come back here to the Bohr model of the atom. And as I said, the Bohr model is not a completely accurate model for how atoms actually are, but it's a useful model for understanding how atoms and the chemical bonds between them work. So the Bohr model has the nucleus of the atom surrounded by a series of electron shells. So the electrons reside in these electron shells. The first period shell can have up to 2 electrons in it. The period 2 shell can have up to 8 electrons in it. And then the subsequent period 3 shell can also have up to 8 electrons in it. So atoms like to have a specific number of electrons in those electron shells. They like to have those shells either empty or full. Atoms that have a full outer electron shell, like helium, which has 2 out of 2 electrons in its outer electron shell, and neon, which has 8, so it's atomic number 10, and it has 8 electrons in its outer electron shell, so completely full. These atoms, these are all very stable and chemically unreactive. So these are the noble gases that don't react very well with pretty much anything. On the other hand, atoms that have either just 1 electron in their outer electron shell, and so they could get rid of that 1 electron and be nice and stable and happy, or atoms that have enough electrons in their outer electron shell, for example, fluorine, which is atomic number 9. So it's got 2 in its inner electron shell and 7 electrons in its outer electron shell. It needs just 1 more to fill up that outer electron shell like neon does. These chemicals are very chemical reactive. They like to either pick up or give away an electron, and they do that through chemical reactions, as we'll talk about. Atoms in the middle, such as carbon, can form lots of chemical bonds because they can pick up or donate their electrons in many different patterns. So, as I said, the Bohr model of the atom is useful for understanding these properties of atoms. However, it's more accurate to represent the electron orbitals as these shells that are shown on the right. And so electrons in these orbitals are present in 3-dimensional shapes surrounding the nucleus. This will be an important concept for understanding why chemical molecules have 3-dimensional shapes, because the bonds that are formed between sharing of these electrons actually poke out in different directions from the nuclei that form those bonds. This concept is going to be a lot more important when you take OChem and biochem. For now, the Bohr model is a useful model for how we understand these atoms. So one way that atoms are able to get a nice stable outer electron shell is by sharing their atoms, or sharing their electrons, with other atoms. And the way they do that is by forming covalent bonds with other atoms. So here we have hydrogen, which has 1 out of 2 electrons in its outer electron shell, and oxygen, which has 6 out of 8 electrons in its outer electron shell. And so hydrogen can share its 1 electron with oxygen, which also shares 1 of its electrons with hydrogen, so that hydrogen has a full shell. Okay? And then oxygen needs just one more electron, which it shares with another atom of hydrogen. So these 2 atoms of hydrogen are sharing their electrons with oxygen, so that all of the atoms in this molecule are filled in that outer electron shell. And so this forms a nice stable compound, nice stable molecule that we call water. So when atoms share these electrons between their different orbitals, This creates what we call a covalent bond, and covalent bonds are the strongest chemical bond that we'll talk about. By sharing those atoms, it creates a very strong association that when we draw chemical structures, we represent as these solid lines between atoms in the chemical diagrams. Atoms are capable of sharing multiple electrons by forming double or even in some cases triple covalent bonds between atoms, such as the double bonds that occur between these two oxygen atoms to make up molecular oxygen, the gas that we find in our atmosphere. So because these bonds are formed by sharing of electrons, the movement of electrons around a molecule, it gives a molecule some important properties, including a property called polarity. Polarity of a molecule occurs when there's an unequal distribution of charge across the molecule. For example, in water, which is a polar compound, that's made up of a molecule that is composed of hydrogen, 2 hydrogens, and 1 oxygen. Oxygen is an element that is much more electronegative. It likes to hold on to the electrons much better than hydrogen does. And so in the compound of water, those electrons are congregated toward the oxygen end. And so the polarity of this molecule is such that there is more negative charge, there is a negative moment at this end of the molecule, and a more positive charge at this end of the molecule. We represent those charges by this little Greek delta sign with either a plus or a minus next to it. So water is a very polar molecule. But other compounds, such as methane, methane is a compound where there are 4 hydrogens, and they were evenly distributed around the central carbon. Carbon happens to be an atom that it's right in the middle of the periodic table. It is not particularly strong at giving away or hanging on to electrons. It's pretty neutral. And so the charge in this molecule is evenly distributed surrounding the entire molecule. And so because this charge is evenly distributed, this molecule is nonpolar. Polar atoms, for example, oxygen, can form nonpolar compounds when the geometry, the alignment of those bonds is just right. So, for example, in carbon dioxide, where 2 very electronegative oxygens are equally distributed on either side of a carbon atom, both oxygens pull electrons equally toward each other. And so the overall charge is equally distributed across the entire molecule. And so carbon dioxide is also a nonpolar molecule. The polarity of a molecule can determine what other chemicals it can mix with. So water is a very polar molecule, and polar molecules interact very well with other polar molecules. So water is a good solvent. It dissolves lots of other polar molecules. We call those polar molecules that dissolve in water hydrophilic or water-loving. Nonpolar molecules mix well with other nonpolar molecules, but they do not mix well with polar molecules. For example, nonpolar molecules such as lipids or fats, they form compounds that we call oils. And when you put some oil into water, those 2 types of chemicals do not mix. One is nonpolar, right? The oil is nonpolar, and the water is very polar. So these lipid droplets that form in the water here are because the nonpolar oils don't mix in the water. The nonpolar molecules are hydrophobic in their water, or what we call water-fearing, and so they don't mix well. And this is a very important concept for understanding how different chemicals interact with each other in biological organisms. Another type of chemical bond that's important for biochemistry is ionic bonds. So many atoms deal with the fact that they want to get an even number or a full outer electron shell by sharing electrons with other atoms. But some atoms are able to form ions where they just go out and give away or grab on to an extra electron to fill that outer electron shell. Two atoms that do this very readily are sodium, or Na, and chloride, or Cl. So chlorine likes to grab an extra electron because it just needs one more to fill its shell, and sodium likes to give away one electron to have a empty outer electron shell. So sodium picks, because it loses an electron, it has an overall positive charge. Chlorine, the chloride ion, and ions are atoms that have extra charge. So chlorine likes to gain that extra electron and becomes a chloride ion. Now, ions that are oppositely charged, such as sodium and chloride, opposites in the case of ions attract. And so sodium and chloride form a chemical that we call table salt. Ionic bonds are pretty strong bonds. They're not quite as strong as covalent bonds, but they are important interactions between atoms that form molecules. A third type of chemical bond are hydrogen bonds. Hydrogen bonds are polar chemical interactions that occur between a hydrogen atom that likes to be positively charged and then an electronegative atom such as oxygen. Hydrogen bonds form interactions between different molecules of water, as shown in this diagram on the left, and give water many of its important chemical properties. Hydrogen bonds are also very important for interactions between amino acids and nucleic acids. For example, the complementary hydrogen bonds that form the interactions between these deoxynucleotides in the DNA double helix. Hydrogen bonds are not quite as stable as ionic bonds, and certainly not as stable as covalent bonds. They are weaker chemical interactions, but they play a really important part in the more complex structures of biological molecules that we'll talk about soon. So water is one of the most important molecules in biological systems. Water has a number of important chemical properties that make it critical for life. One of the things that we talked about already is that water has this polarity. There's a slight negative charge on the oxygen and a positive charge on the hydrogen. And so it is a polar molecule, and it is really good at dissolving or solvating other polar molecules. And so polar molecules dissolve in water, which surrounds all kinds of biological systems. And also that polarity of water plays a role in the different mixing of polar and nonpolar chemicals in cells. These hydrogen bonds of water give water a number of other chemical properties. For example, the hydrogen bonds give water this stickiness of cohesiveness when water molecules stick to each other. And that allows things like this water bug to float on the top of water because the water atoms stick together. They apply a little bit of pressure that keep the water bug afloat. The hydrogen bonds in water also absorb a large amount of heat. And so water stabilizes the temperature of biological systems because it absorbs a lot of heat energy. Water also plays an important role in many different chemical reactions inside of cells. For example, water is able to ionize, where one of the hydrogens ionizes from the water and can form hydronium ions, which are H3O, they're positively charged, and hydroxide ions, which are OH, or negatively charged. And so that hydrogen H plus ion goes to hydronium, and this plays a role in acid and base chemistry. So water, H2O, can ionize into hydrogen ions and hydroxide ions. And an acid is a molecule that's capable of producing hydroxide ion or hydrogen ions into a solution. A base is a molecule that's capable of producing a hydroxide ion. And we measure the acidity or basicness of something by using the pH scale. So pH is a measure of the concentration of hydrogen ions in a solution. The technical measure of pH is the negative log 10 of the concentration of hydrogen ions. Because it's a negative log, a low pH, so a pH of 1, means that there's a very high concentration of hydrogen ions. Things that are very acidic, like gastric stomach acid or lemon juice, they have a high concentration of hydrogen ions and a low pH. Things that are more basic, such as bleach and ammonia, they have a pH of around 10 to 14. Things that are neutral, like water, have a pH of around 7. So buffers are chemicals that are able to resist changes in pH. For example, this carbonate buffer, which is shown in the chemical reaction diagram on the bottom, is able to absorb excess hydrogen ions in a solution by interconverting between different chemicals, and able to absorb changes in the concentration of hydrogen ions in a solution.